Oh, you were going to talk about it anyway.
No, this is SpaceX another launch.
That's what that article is about.
Yeah, it is. It's about. Well, this is just. See, the SpaceX launches are going on so often that I have tended to start ignoring them. But Kurt is crazier than I am about this stuff, and so he actually pays enough attention that he calls my attention to stuff like, which is becoming ordinary. A launch like this is ordinary at this point, so I didn't even care. I wasn't even thinking of mentioning it whatsoever, because I said, hey, why don't you do this? And given the fact that there are 6-7 people here, which for my purposes is not enough for me to do the good stuff that I prepared.
Oh.
Anything that I can do to waste your time with something that isn't as good, so this is.
You're not wasting our time. You're creating joy.
Okay.
Just keep that.
Yeah, this is it. So okay. So we got a Falcon 9. Did it launch 64 satellites?
Yeah.
In this mission?
All different companies.
They didn't show that part.
But they did. It's 64
But some
satellites.
of them are CubeSats this size.
Small satellites.
Yeah. And
Right.
Some are even smaller.
Do you know what
Right.
companies?
Some of them, one is from a high school.
So that's interesting, and that will speak to what I will talk about probably next week. But one of the things that's really interesting is what SpaceX is really doing with its capability. The fact that this sort of thing is going on all the time, and you have no idea how much is going on. But I can give you. Oh, where's my mouse?
Also, this one flew the third time.
This is a third. This is a
almost
Block
black.
5.
It's
full
almost
of-
black from coming back. It gets black when it enters atmosphere, so it gets blacker and blacker.
And then it lands on the ship.
So this is land.
No,
So
on land.
this will be the third time that it's landed. Third time it's taken off. Third time it's landed. The
Listen on them.
Yeah.
Well, sometimes, depending what
yeah. So let's see that. What I've done is I've sped this thing up, so it's a factor of 2 faster than they want you to see it. Okay, and that's because at 11 minutes, this video would take 11 minutes to see, and we don't want to spend 11 minutes at it. So this is twice as fast. 64 satellites. It's going to land and come down. The fact that this SpaceX is able to do this back and forth means.
Has cleared the tower and is now headed upward on its mission to sun-synchronous low Earth orbit. Coming up, the rocket will follow down back to you.
I'm gonna reduce the volume.
Stage separation and SES1 or second reduce.
There you go. The fact that it's able to do this and do it increasingly cheaply means that that what's happening here that I've just noticed, and you think I would have noticed it earlier, but I just noticed that space is becoming a commercial entity. This is an astronomy class, okay? This is not a course in interplanetary finance and interplanetary commerce. But what we are in fact seeing on an ongoing basis is commerce, not astronomy. And what are they going to do with all of this stuff? So I will go ahead and find the landing, if I can, which I think is the most spectacular. See, these little paddles here, these paddles are air brakes, and they're not to be used to stand on. They're to be used to maneuver the spacecraft so it doesn't have to fire its rocket engines in the upper atmosphere. This is used to slow down the spacecraft. And now, well, we'll see where I don't know exactly where we are. Has it turned around yet? Yeah, so now it's turned around. It landed already, hold on. No, come on, I have to go back.
Where did it land?
It landed on a, go back even further. There it is. Okay, it's landing in the middle of the ocean on a barge. The barge, they have a number of barges, but one of them is called, Of Course I Still Love You.
But
Which
where did it go to?
it went up, deposited 64 satellites in Earth orbit, and then came down. The second stage, there were two stages. The second stage was not saved. The second stage was destroyed, but the first stage came down. Elon Musk had at one point said he was developing a reusable second stage. At some point, he decided not to do that. He's always changing his mind. So what he has decided to do now is spend more of his money concentrating on bigger rockets than the Falcon. Because he has determined, and I think, what we're seeing here, step by step, week by week, month by month, is that space is becoming profitable. Some place to go to make money. How do you make money in outer space? I'm going to talk about that, probably not today, but I do have one thing that I can show you. It's on my screen that'll whet your appetite. And that is this. This is an artist's conception. This is of a device sitting on the moon. There's the Earth. This is the moon. And this is a merry-go-round. It's a device that can take two objects on either side of it and spin it around and around and faster and faster and faster and faster. And what can you do with that? You can launch stuff from the surface of the moon into lunar orbit without any rocket engines whatsoever. So if you have stuff on the moon that you want to send up and give to somebody who will buy it up there, you can do it without a rocket. So there's things that we cannot. I just came across this yesterday.
Where would it go?
It would go in lunar orbit, and that object in lunar orbit would then be picked up by a spaceship, which would then ferry it to Earth, or Earth orbit, for whatever purposes it might have. And that's what we'll talk about next week. But I'm saying is, if you're going to build, so Iridium, on the one hand, is building these amazing rockets. I mean, not Iridium, SpaceX is building amazing rockets. Eventually, his amazing rockets will, and the ones he produces in the future, will be used to produce objects like this, sitting on the surface of the moon. And this is there so that people can sell parts of the moon to people on Earth. The thing that, of course, that they're selling would be rocket fuel. But you can make steel on the moon as well. So maybe that. You need how do you make steel on the moon? I do not know. I know there's iron there. So if you have iron and you have the power from the sun, okay, if you have iron and the power of the sun, all you need is a little bit of carbon, which the moon has very little of, as we know right now, but we could bring some. And then you make steel on the moon.
And then what do you do with it?
You build cities, amusement. I don't know what you do with steel on the moon. I don't know what you do with it. I do know that if you can bring enough rockets from the Earth to the moon to bring this stuff that will be sold to other people, that industry will come up with 1,000 things. Think about this. There are on the Earth 7 continents. I don't know why they 7, because it seems to me that Europe is connected to Asia. But anyway, seven continents. This is the 8th continent. it's a little harder to get there, but not that much, especially with guys like Elon Musk. So he makes it easier to get here. And the first thing he does when he gets here is he says, let's make fuel, okay? Because so we can get back and forth, back and forth. So commercialization of space. That's actually what I'm going to talk about next time. But I did want to show you this. Talk about the number of satellites in Earth orbit. Somebody was talking about at the beginning of the class how we're being watched. Yeah, we're being watched.
Who is?
We're being watched by satellites. See, if a certain degree of paranoia, you realize that Elon Musk has launched 64 satellites, and those 64 satellites are watching us. Well, what about the others that they launched previously? This is a picture This is a picture of satellites that are orbiting the Earth right now as we speak. So I've sped up. This is real time. This is real satellites. This is the Earth. And I'll make it. That's stop doing that. So this is the satellites orbiting the Earth right now. I'll zoom in. This is what's watching us. You worried about 64 satellites that are watching us? How about those satellites?
And they're from other countries too, right?
They're from other countries. You didn't know there were this many things up there. There's like 17,000 of them.
Jeez.
17,000 satellites up there looking at us.
How come they don't crash into each other?
How come they don't crash into each other? Well, they do. That's also a conversation for next week. I'm trying to set. I prepared 2 lectures. The thing is, they come together in my mind. I only want to do one of them, and the more interesting one is next week's. So let's stay where I want to stay. Okay, so Elon Musk launches 64 satellites. Who cares? Because that just happened yesterday. Actually, that happened yesterday. So it makes a difference because it happened yesterday. But it wouldn't make a difference if it happened a week ago because that's already old news. If we don't want to get old on our news, so the news that we want to pay attention to right now is that we just yesterday, for the first time, we went and visited a new asteroid.
Yes, I heard
We've been
about
visiting asteroids for a while now. It's getting to be old news. But nevertheless, despite the fact, be careful, there's a camera there. Nevertheless, even if it is old news, it's still news, and it's important news. So this is what it looked like as we got closer and closer to this asteroid called Bennu. And you can see it's diamond shaped, and as
What's the name again? The asteroid?
Bennu, Bennu.
Bennu. Okay.
So you see as we get closer to it, and it gets more and more well defined. You can see that there's a rock sticking up the bottom left, now the bottom right. So this is what it looked like as we were getting closer and closer to it, and even closer and closer to it. This thing orbits, revolves in something like 7 or 8 hours. Here is that same asteroid now. This is as close as we're going to get for a while. We can get really close.
What's the dimension of the asteroid?
It's about 500 meters.
500 meters.
It's big enough that if it came down to Earth, and hit us, it would cause major damage. Major damage means some country would not be there anymore. Okay. And this happens to be an asteroid which, in fact, is on a collision course with the Earth, more or less, not exactly, probably not. Nevertheless, if such an object was headed our way, we would have no way of avoiding it with current technology, because nobody's bothered to build something yet.
How long did it take the rocket that's going there to get to that asteroid? Do you know?
Yeah. How long did it take the rocket that's going there to get to that asteroid?
What I'm getting at is, if it really was on a collision course with the Earth, could a rocket that could destroy it get up there in time to destroy it?
If that really was on a collision course, could a rocket get up there in time to destroy it? And the overall answer is no. And the answer of this, in this case, the answer is still no. But let me show you the video that explains how it got there.
7-year mission to snatch part of an ancient asteroid and
The
carry it
whole
home.
Earth would be destroyed
Its
or
target
part
is
of it.
Bennu, a diamond-shaped clump of rubble, a quarter-mile wide.
Quarter mile.
Asteroids like Bennu were the building blocks of the early solar system 4.5 billion years ago. Most of these chunks of primordial stuff merged long ago in violent collisions to shape the young Earth and other planets. But Bennu survived, pushed and prodded by the gravity of the planets. Today, Bennu has a regular 14-month orbit, which swings it close to Earth every 6 years. But sunlight warms the surface of the asteroid, gradually shifting its orbit in a way that could eventually threaten the Earth. OSIRIS-REx will take 2 years to reach Bennu,
2
then
years.
spend a year mapping its surface. In July 2020, the spacecraft will pick a spot and descend, and try to steal a chunk of the primordial past for humans to study for decades to come. An 11-foot arm unfolds and extends. The spacecraft drops and briefly touches the asteroid. A puff of nitrogen blows a few ounces of ancient dust from the surface. A cosmic high five before the spacecraft retreats to safety. The sample is weighed and stowed in a fireproof capsule for the 2-year cruise back to Earth. As it approaches home, OSIRIS-REx will jettison the sample. Gravity will do the rest. If all goes as planned, the capsule will fall through the atmosphere, open its parachute, and land in the Utah desert on September 24th, 2023. A handful of matter
We should leave that
retrieved
alone.
from the dawn of the solar system. Atoms separated at birth returned for study after 4.5 billion years of wandering. Future missions might visit another nearby asteroid. A larger spacecraft with robotic arms and legs could straddle a 20-ton boulder, grapple it, and tow it away. Then carry it back to orbit the Moon, within reach of Earth and its astronauts. Another step in understanding the birth of our solar system and the world on which we live. And perhaps a clue to protecting our blue and green planet from an asteroid that may one day veer too close to home.
So to answer the question, the first question you asked, how long does it take to get there? It took about 2 years. How long would it take to get there if money was no object? A week?
Wow.
Less? You just have to have the right size rocket. If you have the right size rocket, let's say that this thing turns out to be really nasty and it's headed our way. It's got us in its crosshairs. And let's say we've decided how we're going to avoid it, by how we're going to stop it. And let's say that is a nuclear missile, and there are lots of reasons why that's not the best idea, but let's just say that's the idea. So you send it. You use Elon Musk's big fucking rocket. Oh, I'm sorry, big Falcon rocket, which has now become the big something Starship. Big something Starship, and you use that device, which hasn't been made yet, but which is in fact on his drawing board, and he has said in this last week, I'm concentrating on that now. I'm stepping up on that. That's what I'm looking at. He wants to build the biggest spaceship ever built. With that, you can put a nice load of nuclear rockets. You can put a lot of fuel into that thing, and you can send that thing speeding so fast it will get there very fast. The reason these things take 2 years to get there is because they leave the Earth, they eke their way out of the Earth's atmosphere, then they ride along with the Earth a little bit, and they ride a little ahead, and they go around the sun, maybe once, or maybe twice, while they pick up speed every time they pass either Venus or the Earth, and the Earth gives them a boost, and that gives them, because they couldn't afford the fuel for the bigger rocket. So finally it gets to Bennu, and then it does its business. And it arrives nicely because it matches the velocity. If you're going to destroy something that's coming your way and you just saw it a week in advance, you want to take a direct shot at it, straight line, no passing around the sun twice, straight line, and then you explode a nuclear rocket in its bowels. That could or could not work, depending upon the object that you're looking at in the first place. If it's solid, it might break apart, and that might be okay. You may get 2 smaller pieces instead of 1 big one, and that might be okay. If it's made of sand, blowing it up might not do anything else but blow some sand off the top. And so maybe you haven't changed anything at all. Maybe you want to hit it from the side and change the trajectory, if you have enough time for the trajectory to change before it hits the Earth. I found an interesting statistic. The Earth, in its orbit, moves at a particular speed, 30 miles an hour, 30 miles a second, something like that. For the Earth to move away from itself, let's say this is the Earth and this is a doppelganger, and the Earth, so this is where the Earth was, and the Earth moves to here. This takes 7 minutes for the Earth to get from here to completely away from itself. So all you have to do is to delay the rocket, the rock that's going to hit the Earth. All you have to do is delay it by 7 minutes, and it will miss the Earth. Just slow it down by 7 minutes. If it's up there headed our way, just give it a nudge so it misses us.
Is there a chance it would hit other planets also?
Is there a chance it'll hit other planets? Yes, in the sense that there's always a chance for things that are improbable to happen. Space is very empty. The planets are very small. They're very far away from one another, and basically, if something hasn't hit one of the other planets in 4.5 billion years of trying, there's very little chance that the next year, when you're worried about it, that it will hit another planet. Okay, just because you're paying attention to it. Let me show you what the other planets look like. I mean, what near Earth stuff looks like. Hold on. This this is our solar system, that is our sun, that is Mercury, Venus, and the Earth. These are things that are actually up there right now. Not everything that's up there right now, because there's millions of them, and this thing shows you thousands of things. But these are the ones selected for your amusement that could hit the Earth. These are near-Earth asteroids, and just the near-Earth asteroids. So these are the ones that we have to worry about. And you're worried about it hitting some other planet. You're worried about it hitting Earth. There's plenty of them to choose from.
Is Benno among that cluster? Or
Benno is among that cluster. What they've done is they've looked at this cluster and they say, how easy is it for us to get to these? Not so easy. Which ones are easiest to get to? Which ones will give us interesting information when we get there? And so they narrow it down. So from thousands, they narrow it down to one, or two, or three, or four. There's only a few that make as much sense as Benno to visit.
Those are all asteroids?
Those are all asteroids. Those are all asteroids. Right.
now, they're in the asteroid belt, isn't it?
No, they're not in the asteroid belt.
They're not.
No.
They're closer.
Yes.
The asteroid belt is further out.
Yeah. Look, this is the asteroid belt. Okay. This orange swath there. That's the asteroid belt. These guys are closer.
Closer. Yikes.
Right? Yeah, it's a scary space out there. Think of this. As you look at this, say to yourself, 4.5 billion years ago, when the planets were being formed and the sun was being formed, the solar system looked like this, but 1,000,000 times worse. Okay? And everything was hitting everything. And as a result of everything hitting everything, you got planets. You got the sun. You got planets. And after a while, things stopped hitting each other because everything that would hit each other had been hit and absorbed. That's how the Earth was formed. The Earth was formed by swarms of stuff hitting each other and getting bigger. Can you imagine this planet? Or everything around us is nothing more than a conglomeration of things that hit each other,
Wow.
right? I mean, that must tell you there was an awful lot of junk up there. And now, how much is hitting the Earth now? Well, actually not nothing. This is amazing. See this chart? This is things that have hit the Earth between 1994 and 2013, okay, that are anywhere between 1 meter and 20 meters wide. That's the width of this, the length of this room, okay, so somewhere between this big and the length of this room, that have hit the Earth during this time period. And the size of the dot indicates how big it was. The color of the dot indicates whether it hit during the day or night. Okay? So if you think the Earth isn't getting hit, it's getting hit all the time. These disintegrated in the Earth's atmosphere because they were too small, because they were only 20 meters in diameter. Make them a little bigger and they don't disintegrate. Maybe they explode on the way down. Make them a little bigger than that, make them 3 times as big as 20, and they hit the Earth and make a crater. Make them even bigger than that, and they cause damage, big time damage. So with a little bigger size than this, a city, make them even bigger. A country, make it even bigger. Wipe out all of civilization, depending on your choice of size. The bigger it is, the less frequent it is up there. Smaller ones are frequent. You can see that with the graph. Smaller ones are more frequently hit the Earth. Bigger ones, less frequently hit the Earth. And that goes on for all sizes. As you get bigger, the frequency gets smaller. Frequency of hitting it. That doesn't mean it goes to zero. And the fact that we know that there are millions of potentially hazardous asteroids out there doesn't seem to have any effect on the purse strings of the governments of the world in terms of building something that might protect us from one of these things.
What would that be?
What would that be? It would be a rocket with a nuclear tip. Okay, but do we have a rocket with a nuclear tip that's ready to go? Something the size of a Saturn V rocket ready to send giant nuclear bombs to save civilization? No, we don't have such a thing. If it did happen, we would need years, or at least a year, to do that. And some of these things we only spot within days, sometimes within hours. Things have hit the Earth and caused damage that we haven't seen until after it hit. Then we see, we could have seen that we would have known that, but we didn't see it because you weren't looking in that direction. To give you a graph. Where is it? I took the data from the web, talking about we call these things minor planets. Anything that's floating on in outer space, a word that covers them all is minor planets, no matter how small they are. Big asteroid, because they could be bigger than an asteroid. Let's look at how many they found as a function of time. This is 1995, and we found this many. And over time, we found this many. And if you notice, the thing that's interesting about the graph is it shows no signs of leveling off. If we found them all, this graph would start to do this. But we haven't found them all. What this graph tells you is that we're nowhere near finding them all. And the process of finding them all requires more money to be allocated in order to find them. And that money has not been forthcoming. So we could still get hit. We could get hit with things we don't see coming, and we do not have the resources to stop it if we do see it coming. Yes.
Why did we find them faster?
What? Because in each case, more and more money is being applied. The technology is, in fact, increasing. New objects are being deployed to do this on an ongoing basis. People are getting more and more serious about it. For instance, there are devices that do nothing else but look for this stuff and record it and do the whole thing in the computer without anybody ever paying attention.
So they may also get smaller if we improve the technology. Yeah?
So the what?
They may also get smaller, the one we find.
So the ones we find may get smaller as we improve the technology, but there is a problem, and that is some of these objects are coming from the wrong place. Some of these objects are coming directly at us from the vicinity of the sun. And if you point a telescope at the sun, what you do is you blow out the electronics. So you don't look at the sun, you look away from the sun. Of course, you should be looking at the sun because that's where they're coming from. Okay? So you need to have really good telescopes that look away from the sun just a little bit, and they should be in outer space to begin with. Okay? Because if you're trying to spot an asteroid during the daytime on the Earth, as you all know, the only thing that you can see is the sun. That's it. You don't see stars, sometimes you can see the moon, but that's it. So you gotta, if you're gonna see something coming at us from the sun, you better be up in outer space in order to do that. And that costs money to put something out there to do that. But they're putting more and more things out there to do just that.
They're looking at the wrong places if they can't find
They're
it.
looking in the wrong places, yes.
Yeah.
Yes. Yeah, I was.
Is this what Kepler did?
Kepler was never the Kepler spacecraft was never looking for space debris. The Kepler spacecraft had one mission and one mission only: stare at one spot in space for 4 years. The same spot for 4 years. For 4 years. That's all it did. It didn't survey the sky. It just looked at that spot. And if something whizzed by, it would be ignored. Because they were only looking for things that remained in that spot and got brighter and dimmer in that spot. So anything whizzing past would be ignored.
And it keeps going up the graph until you find it all, then it'll turn to the right.
Yes, the graph keeps going up until they find them all, and then it will go to the right. Right. But until this tells you that we are severely nowhere near finding them all. You know, and there's one thing that's true. I can tell you for a fact that if in the absence of observation, but just theory alone, this graph goes like this forever, because the smaller the particle, the more there are. So exactly what size are you worried about? If you're worried about this size, then there's something that's even smaller, and there's 10 times as many of them as there are of this. So you're not worried about this, but there still are. That graph goes off like that no matter what. It's what you can see. So at a certain point you say, my cutoff is not this, I'm not interested. My cutoff is this, okay? So if your cutoff is this, then theoretically the graph, the graph does that. And when you observe it, you should find the same thing. It should level off. Yes?
Am I reading that right? That number on the left is 200 and something million?
Yes.
Right? Wow.
Yes. 210 million objects whose orbits are known. Right? When I showed you that picture before, and I showed you all those things circulating around it, and I said, that's just the ones that are hazardous to us? And you thought, no, that couldn't be right, Laird. That's everything. No. That was just the ones that were hazardous to us. The number 210 million, if you put that on a graph, you might as well pick up a piece of white paper and say, here's all the things that are dangerous, because it would cover the paper entirely. Right? So you can't represent that. You have to represent a subset of that in some fashion. Yes?
Within the boundaries of space, the Milky Way is here. Let's say it's in the center of the screen. In what direction would we be looking for? We were looking for the next galaxy, like Andromeda. Which, north, west, east, south?
Okay, so you're asking a question. You're asking a question: in which direction would Andromeda be in this context? The problem is there's no context in which your question makes any sense. I have to change the context for your question to make sense. Okay, so I can do that. Is there some context that I've already shown you? Let's see. It's hard to bring. Well, let's see. I have one context that I was showing you. I mean, I don't want to bring up a whole new display that you haven't seen before in this class today, but I think I can bring up the impact avoidance thing. This one. Okay, so this one has at least a solar system here. So there's the solar system, and the Milky Way isn't shown, but it's off like this somewhere. Okay, the Milky Way is like this, and Andromeda, the nearest galaxy, major galaxy, is somewhere, possibly here, possibly there, possibly. I don't have any idea where it is on this because there's no context in the sense.
Scientific directions of any which way?
A person who knows the solar system better than me could, you looking at this diagram, place the and also knowing where the Earth is at a particular time, could say, aha, Earth is here, and I know that if I look in this direction, I'll find Andromeda. Okay, but maybe if the Earth is there, I need to look in that direction to find Andromeda. So a better astronomer who looks up could tell you the answer to that question. Yeah, and I have lots of displays which will do that, yes.
But in this magnification, Andromeda on this graph would be like on the west coast or something, yeah.
On this magnification, Andromeda would still show up. But
I mean, it's a distance in...
Andromeda, in terms of distance,
Would be on the west coast.
Andromeda would be, distance-wise, on this graph, would be ridiculously far away. You know, Kurt is saying West Coast, maybe China, maybe who knows where Andromeda would be in the context of this scale.
One more question. And then what I read, that if the solar system and all the stars and planets are moving, they're moving in the direction of Hercules at 7 miles a second.
Okay.
So if there's no boundaries in space, then it's going to go on forever?
You're saying that the solar system is moving in the direction of Hercules, the constellation Hercules, that's 7 miles a second. And I'll take your word for it, because I really don't know where I am in the universe. See, so that's one of the things. Yeah, real astronomers who look up know where they are. I never look up, so I never know which direction I'm headed. Okay, so you're telling me we're headed in the direction of Hercules. Absolutely, positively, reasonable sort of thing. 7 miles a second sounds good to me. And what is it you're saying? What is it you're saying about that?
Yeah, so if we're heading in that, well, what direction is Hercules?
Again, I don't know where Hercules is in the sky. I have no idea.
Again, it comes down to the astronomers.
Right, the observational astronomers. Yeah, see, observational astronomers, there are two kinds of astronomers. There are theoreticians who look down, and there are observational people who look up. And they look up, and when they see the sky, they see lots of stuff. All I see is what you guys see. I see a lot of stars. I don't see any constellations except the Big Dipper and Orion. And Orion's good in the winter, I can spot it. In the summer, I see nothing except the Big Dipper. I don't even know what the constellation of Hercules looks like. What does it look like? But I have software. Let me just show you. So I have software, Starry. Okay, so I bought a piece of software. It cost about $65. And it gives you the night sky. So, Starry Night Enthusiast is one. There are other simulations which are free. Just happen to know this one. Also, I shared the cost of it with Kurt. We are currently one of us is pirating the software. The other one has it illegally. I don't know who's the pirate. So find Hercules. There's Hercules, okay, in the sky. Problem is it's daylight, so I have to change my viewing location from the surface of the Earth to the center of the Earth, where sky doesn't make any difference. You pretend you're Superman with X-ray vision, and there's Hercules in the sky. And, because I don't have any ground reference now. I should go back and take a look at a viewing location. I should go back to the surface of the Earth and go to that location. There I am, and this is Central Park on the Great Lawn of Central Park. And if you look in the southwest direction, now you'll find Hercules there, and hours from now, let's try it at 11 a.m. Where's Hercules now? I will now find it again. And Hercules. And it's not currently visible from my location. Okay? So I'll have to look at it at the best time, but that's during the day. So I can find Andromeda, I can find anything in the sky. That's why I don't ever look up. You want to, let's see where Andromeda is, okay? Because find Andromeda. Okay. It's going, it's going, it's going. There's Andromeda. It's in the northeast, and it's low in the sky, and I don't know whether it's coming up or setting at this particular point. I could run time forward and see what happens. I'm running time forward. I'm running time forward, and sure enough, at 6 o'clock in the morning, 6 o'clock at night, Andromeda is visible in the sky at that particular place. And now Andromeda is setting, and daylight is coming back. But Andromeda is going to come back, and there it comes back again in the sky.
There's a different places,
Yeah,
different
right.
times.
You see why I don't look up? It would waste my time.
Yeah, but I can see why you got that software.
Right, right. So I can answer questions like that all the time. There's basically, from my point of view, if you can derive the answer, there's no point in studying it. I'm a physicist. I'm not a doctor. A doctor would have to memorize an entirely long length of things. As a physicist, I had to memorize virtually nothing. And everything that I needed to know, I could figure out, because it's based upon laws that are immutable over time and space. So I can figure out anything. I don't need to know where Andromeda is. I can look it up, you know. Does that answer your question? Did you have any other question about where something is in the sky, as long as we have this thing up?
Orion, where's
Orion.
The only thing that came to mind.
Yeah, Orion. Orion is good in the winter, okay, because that's the only thing I actually can spot in the sky. And there it is.
Oh, it's close by.
I'm going to stop it because otherwise it'll disappear. So this is 12:14 a.m. And Orion is visible in the south. So if you're walking down a country road, and I happen to have a country road in which passes by my house in the country, and which is obviously where the country road would be, and as I walk down that street, Orion is always in front of me. That's how I know where it is. But it's hard to spot it. I mean, it's not hard to spot it. It's hard. You need to know stuff about Orion. I don't, but I'll tell you a few things I do know about. I know, for example, that this star here is a red giant star, gigantic star, Betelgeuse. And I know this star down here is a blue star, Rigel. And they're both gigantic stars, but one is very, very old, and this is very, very new.
But the blue one is new.
The blue one is new.
Rigel.
Rigel, or Rigel.
It's
Right.
on Star Trek.
Of course, they use the names of things that people are familiar with. And then Orion has a belt, okay? and Orion has a dagger hanging down, or a sword hanging down from his belt. And in the dagger, there is a middle star right there. And you notice I have a little circle around it. That little circle I put there because it is the exact size of the moon. So the moon is this size in this display. So if I pull out, the moon gets smaller. If I pull in, the moon gets bigger. So the moon, it gives you a sense of how big a thing is in the sky compared to the moon, and I always have the moon with me in every display I have.
I don't know, I've got a question. I don't know whether it's relevant to this class or not. But who gave these constellations these names and dreamed up these figures?
You're asking who did it?
I mean, why would, yeah, who did it?
Who did it?
Do you know who did
Yeah,
it?
I do. All of mankind, throughout the ages, in various cultures, gave it various names. And we happen to have the ones in our Christian culture that derive from the Greeks and Romans have given to us. But every other country in the world has its own names for these things, if they can see it with the naked eye. And it's been true forever. Every planet has names in different languages. You know, everything that's in the sky has names in different languages, and it comes down, and the who is left in unrecorded history. I don't know. The Indians have nice names for these things. They have a nice name for this one. This is interesting. You see this one? With your naked eye, you can see two amazing things. Again, coming back to Orion, which you can see in the night sky. In the winter, look along his dagger. The middle star of the three stars in his dagger. Take a pair of binoculars and look at it, because it becomes, if you can see the moon through a pair of binoculars, you can see this through a pair of binoculars. So whatever I'm showing here is visible to you with a pair of binoculars. Well, the whatever that I'm showing you here is called the Orion Nebula. And it is one of the most spectacular places in the sky, visible to the naked eye and through a pair of binoculars. It is a stellar nursery. It contains tens of thousands of stars that are currently being born in this colorful gas cloud, which is not colorful to the naked eye because your naked eye doesn't pick up things too well in the dark. So you won't see the reds and the greens and the blues. You'll see the white. But you will see a nebulosity through your telescope. Not that I've ever actually done this. I'm just working from theory here. And I think I will do it. I have a very nice pair of binoculars. I'm going to try this weekend. I'll report back and say what it looks like. But this is the Orion Nebula. If it looks like this, a square in there, it's because there's a flat photograph that's pasted there. Yes.
What size binocular would you use? Like
Any size
20 by
binocular.
50?
What? 50 would be great.
20 by 50 is good?
The 20 by 50 that tells you how big the objectives are. The magnification, be able to hold it steady, shouldn't be over 7. But the 50 will give you a lot of light,
Right.
so that you'll be able to see it much better. Okay, so the big binoculars will give you a better view, not a bigger view, but a better view, with more light coming in, so you'll see more features. So 20 by 50 is very good to see that. Okay, I'm going to conclude the class because I want to get to the museum, and so I have to pack up.
You want to pass around the
Oh,
attendance?
and while I'm doing that, do the attendance sheet. Thank you.
We don't even have to send a rocket ship through a nebula.
That's because the nebula is tens of thousands of light years away.
That's all.
And we haven't gotten out of our solar system barely. So the reason we haven't gone there is because it can't go there. Can't go there. It's too far away by a lot.
many light years?
Let's say 1,000 light years away.
Now,
Right, 1,000 light years away.
We are so primitive.
We're not primitive. That's not because we're primitive. It's because you're talking about magic now. We don't have magic. If we had magic, we could go there. It may take magic to get to the stars. There's no known technology that we can even conceive of can get us there.
I used to be in
Well, all that dust they're collecting should be very interesting.
not magic.
It is magic because we don't know how to do it.
Right, but if
And-
physicists keep on working on it,
As Arthur C. Clarke said once, he said, technology of any advanced civilization would be like magic to us. And since
Yeah.
there is no way that we can conceive of how to do that, it would have to be magic.
okay.
Because we
That
don't
sounds like
have
it.
any way of
What
thinking
you
how to
said.
do that.
I really hope that I get born into another entity that can go to the stars. I don't even believe in reincarnation, but if it exists, that's where I want to go.